Hi, everyone. Welcome to the GIST Sea Level Rise seminar. We're very happy today to have Dr. Karina von Schuckmann. She is a physical oceanographer specializing in ocean climate monitoring, working at the Mercator Ocean in France. And her interest lies in understanding the role of the ocean and its interaction within in the Earth's climate system, its changes and underlying processes involved, and how they can be best observed using in situ remote sensing, monitored using reanalysis and operational systems, and estimated using analysis approaches, ocean integrator development in support of a sustainable future development. She is working on the Earth energy imbalance and the Earth heat inventory, particularly concerned with the role of ocean warming under climate change. And she is currently, amongst other things, lead of the Copernicus Marine Service Ocean Reporting Framework, lead author of the IPCC special report on oceans and the cryosphere, I believe. And she has contributed to the recent IOC Global Ocean Science Report, and is a member of the European Academy of Science and the GOOPC panel. She earned her PhD and diploma in theoretical and physical oceanography from Christian Albrecht University in Germany. And today she will be speaking on the topic heat stored in the Earth system between 1960 and 2020. Where does the energy go? Welcome.
Thank you very much, Patrick, for the introduction. And I would like to thank you very much for the opportunity, particularly Gavin, to provide this seminar today. So, which already introduced is on the heat stored in the Earth system between the 60s and today, and to leveraging the question, where does the energy go? I would like to highlight that this presentation is based on a work which has been done by a huge number of experts, and without their expertise and their help, it would not have been possible to gather all this information together, provide an overview on the Earth heat inventory based on the different observing system capacities, including also model analysis and evaluations and uncertainty discussions. So we have just published yesterday, so it was a coincidence on the timing, on this second cycle on updating the Earth heat inventory up to 22. And I will provide now the background of this work, and also highlight that all the data are also public available. So I would like to start with a general background. So the Earth's energy budget, it's determined by the main flows of energy into and out of the Earth system. And this in turn provides a state variability and change of the climate are to a large extent driven by the energy transfer between the different components of the Earth system, like between the atmosphere, the ocean, the land, the ocean, and the cryosphere, etc. And this energy flow then in turn can alter clouds, that can alter weather patterns and external and internal climate forcing, and those can temporarily in turn alter the Earth energy balance for periods, but also of days, but also up to several decades and even longer, depending on the forcing. So the Earth energy balance is one of the most fundamental conditions for making planet Earth conducive to sustaining life. So this balance, this natural balance at the top of the atmosphere, is defined as the perturbations of the equilibrium Earth energy budget, which arise from internal or external climate variations. And those in turn can create a positive or a negative Earth energy imbalance at the top of the atmosphere. And those are manifested as a radiative flux imbalance at the top of the atmosphere. So how can this balance or the natural quasi-equilibrium be altered and changed? So this can be done through climate forcings. So these different variations of the Earth's energy budget are determined on how the energy flows govern the climate response to a radiative forcing. So there are different forcing agents which could induce at different timescales a change of the Earth's energy budget. So this can be happen at subseasonal to decadal scales, such as, for example, through climate variability patterns, for example, like El Niño Southern Oscillation, which can use either positive but also negative Earth energy imbalance, depending. It can induce negative Earth energy imbalance to large volcanic eruptions. And there are also other forcing agents like acting at decadal and longer timescales, which can changes in solar output, including negative or positive Milankovitch cycle, negative or positive, or as currently the case for human-induced changes inducing a positive Earth energy imbalance. So understanding the changes in this Earth energy flows helps to understand the main physical process which are driving climate variability and which are driving climate change. So today, as mentioned earlier, a major climate forcing is ongoing. And so as currently the recent assessment from our 6th report published in 21 is that the human-caused net positive radiative forcing causes an accumulation of additional energy heating in the climate system from the current prevailing positive Earth energy imbalance. And an estimate is provided here where we have on the left-hand side the radiative forcing from the different forcing agents and with a linkage to the Earth's heat inventory provided by the different components and the ocean, the ice, land, and the atmosphere. I would like to further discuss this kind of estimates and I'll particularly leverage the question how we can monitor and how we can evaluate the Earth's energy imbalance. There had been different discussions ongoing. We had also prospective activity also on WCRP and Cliver and discussing these different possibilities to monitor and to evaluate the Earth's energy imbalance. And so I would like to particularly draw attention today on the way of evaluating the Earth's energy imbalance through the estimate of the Earth's heat inventory, which is providing an insight on where the heat is stored in the climate system. Another opportunity is to estimate the radiation at the top of the atmosphere, so through direct remote sensing estimates, which provides today the best estimate in terms of temporal variation of the Earth's energy imbalance, is somehow anchored by an estimate of the Earth's heat inventory measured from the ocean, and hence has larger uncertainties in terms of the absolute value of the Earth's energy imbalance. And there's a possibility to estimate an inventory of the Earth's surface budget, which provide also an estimate and can provide an estimate theoretically on the Earth's energy imbalance. But as there are several parameters from the Earth's surface budget derived and not directly measured and also rely on different assumptions, there is today a huge uncertainty which reveals if one is going through an inventory of the Earth's surface budget, leading to uncertainties which are much larger than the value itself. For example, for a value of 0.5 to 1 watt per meter square, there's a current uncertainty between 10 to 20 watt per meter square while using this approach. However, there are other opportunities, and this is, for example, to anchor the surface budget approaches to constrain the different other radiation components of the Earth surface budget. But I will not further discuss this today. And of course, then the climate models, which will help to the fundamental testbed of the climate models, and also further understanding on the processes and the changes behind, but also vice versa, of combining the different methodologies, which in turn might lead and can lead to opportunities for validation, but also for different constraints. So I want to, as I said, I will put the emphasis on the Earth's heat inventory. So what is the Earth's heat inventory? To repeatedly and clearly define it again. So the surplus energy from a positive Earth energy imbalance, mostly in the form of heat, in the climate system determines the Earth's heat inventory. That is encompasses storage of heat in the ocean, the land, the atmosphere, and the heat available to melt ice in the cryosphere. So as a consequence, there's a continuous warming of the ocean, a continuous warming of the land, continuous warming and hence melting in the cryosphere, and a warming in the atmosphere. The majority of this warming had been estimated to take place through the huge storage capacity of the ocean, which is about 90%, and the other components are available in order to melt the ice, to warm the land and the atmosphere. From a global perspective, those numbers might appear to be very small as compared to the big ocean component, but this smaller number here on the cryosphere aspect, at least, which is also considering not only land-based one, but at least for the land-based ones, is making up today 60 to 70% of global sea level rise. So it's a relative discussion one has to open while looking at the Earth's heat inventory and also its implications for change. So we have stated in this work together that the Earth's heat inventory provides a measure of the Earth's energy imbalance. And that in turn allows for quantifying how much heat has accumulated in the Earth system and where that heat is stored. So this Earth heat inventory is really the best available estimate today of the absolute value of the Earth's energy imbalance. And together with the direct measurements from space at the top of the estimate, both provide a valuable tool in order to further monitor and further describe the Earth's energy imbalance variation and change. Then the integrated view of effective relative climate forcing, it's the Earth's surface temperature response and the climate sensitivity. It informs about the status of global warming and replies to the question how much heat is in the pipeline and how much we have committed already to climate change. It allows for assessing the status of the global climate observing system because it considers the overview of the different components in the Earth system and how we are able today to measure these different changes in the entire Earth climate system. And it enables concerted international multidisciplinary collaboration and also discussing advancements in climate science, because here a community, a multidisciplinary community from an international institution was coming together to discuss together one specific topic in a concerted approach. So we were following the question and this approach where the energy is going. So for this purpose, as you might guess, we have then worked together in order to think of and work on the different estimates from the observations when possible to derive, for example, the heat available to warm the land, the ocean heat content, the atmospheric heat content, and the heat available to melt the ice, which will then provide the full picture of the Earth's heat inventory today. So how have we done this? So I will start with the heat available to warm the land. So we have started with our first assessment in 2020 to concentrate fully on borehole temperature profile measurements, which in this method had been updated today for this new publication to update on the one hand on the methodology and also improved evaluations for the uncertainty levels, but also to extend up to the year 2020. So this is providing an overview in red on the global cumulative heat storage within the continental landscape since the 60s, and also the confidence interval in terms of reflecting to the uncertainties. On the upper panel, you can see today the situation of where the different measurements sits at a global scale, and also with relevance in terms of the time frame when these measurements have been taken, leveraging again something which I highlight later on, what the opportunities are today, but also what the caveats are in terms of limited observing system recommendations. And also something to highlight and to mention again, I will do it later again, that today there is no clear global scale data repository for this type of measurement. What has been done also, and this has been all done by early career scientists, Francisco Cuesta Valero, who has taken together this community as a baseline in order to support our work with a peer-reviewed publication in parallel, which had been also accepted already. So it's the heat available to warm land, and we have not only looked at these borehole measurements on the ground, but we have also looked at the permafrost and the inland water storage. For this purpose, we had to rely on the different combined use of measurements, but also particularly for models. And this is due to the fact that there's a very limited availability of observations available today. So what has been used is ERA interim, so atmospheric reanalysis, paleo simulations, the cryogrid little permafrost model in order to get an estimate on the permafrost heat storage. So this is summarized together in another paper and also published a data set in Nitzborn et al. And then for the inland water storage, we rely only on simulations. So there had been the use of 4 simulations and 4 lake models, which provide then an insight in the inland water heat storage. And this had been published under Van der Kielen et al. 2020. So this is the result. So again, this is also published in Cuesta Valero in 23, just recently, providing the overview of these different estimates for the land component, considering again the ground, the inland water, and the permafrost. And here you can also see the different results by considering those together for the different contributions, with a major contribution that the continental landmass is stored at 23.9 during the period 1960 to 22. And so the ground stores 90% of the continental heat storage, and the inland water bodies and the permafrost degradation accounting for 0.7 to about 9% of the continental heat respectively. So this is a kind of overview in order to provide this information. Then I would like to draw on the observing system. I think it's an important aspect to also highlight what can be done, what is needed, and what are the recommendations for the future. So the issue here that there's a lack of subsurface temperature profiles, particularly after the year 2000 and in the Southern Hemisphere. There's no existing international data acquisition and curating efforts, as I mentioned earlier, for the borehole temperature profiles. The recommendation is there's increased sampling of subsurface temperature profiles, implementation of international data acquisition and curating efforts. And the impact is very high because with improved knowledge of the surface energy balance together with the soil conditions, is fundamental to understand the evolution of the land-atmosphere interactions, affecting important climate and meteorological phenomena, such as surface temperature increase and extreme temperature events. Then I would like to draw on the issues for permafrost. So it's defined as a required heat to change the mass of ground ice at a certain location. But in order to properly do this, there is today a lack of ground ice and liquid water content data. The current monitoring system for permafrost soils is focused on soil temperature. And this is again linked to a scarce data sampling. And the estimate of heat uptake by thawing from ground ice is estimated from a model. So the recommendations are straightforward: improve the sampling for soil temperature, establish monitoring for ground ice and water contents, improve the simulations allowing for the inclusion of other relevant processes, and leveraging again the impact that the permafrost carbon feedback associated with the permafrost degradation will add additional greenhouse gas into the atmosphere. And permafrost thawing is identified as one of Earth's tipping point for climate, and costing could be severe. So hence, we should be ready to at least monitor what is happening over there. For inland water storage, the limitation for lake bathymetry. So as I said before, we are really relying only on model results for this estimate. The global scale long-term observation-based estimates are still lacking. So there's opportunities from upcoming remote sensing missions, and also the river water storage should be improved. Also here the impact is high because the increase in the heat uptake by inland water bodies are causing a lot of change. They can impact ice covers and lake certification, but also degrading water quality, increased algal blooms, deoxygenation, and that in turn threatens the food security of communities which rely on the freshwater fisheries, for example, and other ecosystem services. Then I would like to come now to the atmospheric heat content. So what has been done here in order to obtain the estimate for the atmospheric warming aspect of the Earth inventory is to combine atmospheric reanalysis together with remote sensing data. And you can see here the results from 1960 up to the year 22. And on the right-hand side, you can see the different changes of the warming, which has increased also in the atmosphere over different decades, and which has been also leveraged to be shown in different regions on the global areas, here for the northern southern hemisphere and for the tropical areas. And so what has been done here is that from the 80s to 2020, there had been different reanalysis used, and also 2 different observational data sets, which are mentioned here from the 60s. So there's a small error, sorry. Then the atmospheric heat content issues here. The observations for atmospheric heat storage rely on unsustained GCOS, which particular imminent data gap risks admit to high latitudes, which is also a question on the orbital choices. Earlier, before 96, the estimates are from reanalysis only. And the recommendation is to sustain and enhance the current operation long-term monitoring system. There's also an urgent need for satellite missions in high inclination orbits, as I mentioned earlier. Archiving of data and metadata is important, and the impact is also high because of widespread and rapid changes, which are ongoing in the atmosphere due to human-induced climate change, and that is rapid over the recent decades and has high impact on human lives. The other aspect is on the heat available to melt the ice. So also here we have worked with a combined use, depending on what are today's capacities of the global climate observing system to capture this part of, as you might say it earlier, as a small number in the global perspective, but with the huge implications at a local perspective. So the regional perspective. So the combined use of in situ and remote sensing observations have been used in order together with reanalysis and also with model data, with the assumption that the energy uptake by each component is directly proportional to its mass loss. Particularly, we could benefit here that there are a lot of internationally driven initiatives already ongoing, which rely more on the mass aspect, was motivated by the need for sea level budget approaches, for example. Not all, it's not the only reason, but it's one of the major reasons. And so we could rely, for example, on these activities like IMBI for the ice sheets or GLAMBI for the glaciers. So, and work with these experts together and extend our analysis for the energy uptake evaluation. So, for example, for the ice sheets, we would also need to consider the floating aspects, for example, which are not considered, for example, in the sea level budget. So in this study, the heat uptake over this period is dominated by the mass loss from Arctic sea ice, glaciers, and the Antarctic and Greenland ice sheets. And so this is an overview on what we could achieve. And this data is starting in the end of the 70s. I think it was 78. So what's the issue here? Many issues, because on the first hand, we have many components, but we also have many data gaps. And there are many assumptions we had to take in order to open a new page to look at these mass changes from a discipline perspective, that is to evaluate and assess the heat available to melt the ice in the cryosphere, and that for the different components of the cryosphere. This includes this cross sampling, and there's a non-sustained observing system elements. There's a lacking ice melt below sea level and firn and the ice temperatures. So there's systematic bias in cryospheric energy uptake estimates, for example. Many recommendations have been done. So sustained remote sensing with polar focused orbits. So it's similar to what has been said also for the atmosphere, but also including multi-frequency altimeters in order to capture, for example, the albedo change, the sea ice area and thickness. Also, there was a big vote for earlier launch, for example, of Sentinel-1C for monitoring ice speed change at higher frequency. There's a need for reliable gravimetric, geometric, and ice velocity measurements, need for ice thickness and extent snow firn thickness and density, open data access, coordinate international efforts, and for monitoring the ice loss and related energy uptake. So the impact is high, as you might agree. We have listed some here, but this can certainly be further extended that the changes in Earth's cryosphere affect almost all other elements of the environment, including the global sea level, the ocean currents, marine ecosystems, atmospheric circulation, weather patterns, freshwater resources, and the planetary albedo, and the cryosphere hosts several tipping points. Then, last but not least, is the aspect on the ocean heat content. As mentioned earlier, its biggest component from a global perspective. So what we have done in this update is a new assessment, which is now based on 50 different international in situ-based products. So all products might have differences, and I can reply to several questions on why this is the case. What we have approached here is to use these different estimates and go through an ensemble mean approach with related uncertainties, which have been shown here for the different depth layers, starting in the 60s up to 20. And these they all show an increase in ocean warming over the past 5 decades at specific rates, which are agreement, for example, with what has IPCC just provided. I want to strike here that we have limited our estimate to the upper 2,000 meters, and also that we have excluded bathymetry areas of 300 meters. Everybody has done the same in a coherent manner, and that we are in a near global aspect between 60 degrees south and 60 degrees north, choices which have been taken simply due to observing system limitations. Just a quick overview on the evolution, what is behind this time series. So there's evolution of the observing system. Again, the choice is made. And for historical measurements before this new century, there was a majority of data driven by kind of XBT data, so shipboard measurements. Here's another more modern way of deploying the XBTs. Then there are also direct shipboard CTD measurements, and that made the majority of the observing system together also with some mooring surveys. And then since 2000, you might be all aware on the implementation on the revolutionary part of how to observe in a hydrographic sense at the ocean with temperature and salinity measurements covering between 60 degrees north and 60 degrees south, and a 10-day frequency and 10-day frequency and what do I want to say? 10-day frequency. Yes, and 3 months resolution. The global ocean, and this program had been launched in the year 2000 with the first deployments. I think 99 was also the very first deployment, test deployments. Now reaching about 80% in the year 2005, and in November 2006 there was initial 100% target achieved, and this which had been now maintained until today, with currently from last year, but it's still around the same number of about 4,000 floats currently measuring the ocean. So then there's another way. So I just mentioned here the in situ observing system, but there's also a different way in order to obtain estimates of the full depth ocean heat content change, and this can be done from space. There are new estimates available where you benefit that you have also altimetry for sea level and the ocean mass available, and so you can derive an estimate of full depth ocean heat content while applying the sea level budget approach. So there are different estimates here. I mean, you can check the slide later, or this table is also included in the published paper, but there you can see an overall agreement with uncertainties from these different approaches. And this is also a figure I like very much. It's providing you an overview of all the different estimates we have included in the study for ocean heat content, which had been distinguished between different depth layers, the upper 300, upper 700, upper 2,000 meters, and have a spot focus on the 700 to 2,000 meter depth layer. And as a result, you can see that there is a continuous and even increased stepwise storage or rate of change in the heat storage linked to the Earth, then directly, which can be directly linked to the Earth's energy imbalance, and also with an increased redistribution of heat into the deeper layers, so which is nicely indicated here in this intermediate depth layer visual. So issues are here. Decadal-scale increase of the Earth's energy imbalance is currently observed, but with large uncertainties. So the global ocean observing system currently undersamples the ocean measurements polewards of 50 degrees latitude in deep ocean and in some shallow areas, as mentioned earlier. Technical developments are needed in order to improve this. There's a lot of activities going on with the first implementation for a deep Argo component, and also there are new developments which are able to detect, for example, bathymetry, and can then also go closer to the coast. And there's continued efforts to bias correction methodologies, which had been particularly in the instruments from the historical measurements before Argo, uncertainty evaluations, data recovery and processing of historical data sets. And the impact is high because it's a major component of the Earth's heat inventory and hence the Earth's energy imbalance with adverse impacts from ocean warming. So putting all this information together as a global scale community, we then tackle the question, where does the energy go? So there's a total heat gain estimated from 71 to 22 of 381, plus minus 61 cetajoule. This is providing an estimate that of this part, 89% is going to the ocean, 6 into land, 4 in the cryosphere and 1 in the atmosphere. And then one can be derived into an Earth energy imbalance estimate at the long term, which is around 0.5 watt per meter square, and which has a significantly increased over the most recent decade, which is around 0.8 watt per meter square. So both cycles of the Earth's energy interrelation have shown that the Earth's energy imbalance increased over the recent decade. Also, other studies, for example, the radiation fluxes and the geodetic approach suggest an increase in heat uptake since the year 2005, most markedly in the recent years. So we can ask the question, how and why did the Earth's energy imbalance change over the past decade? And there had been several studies ongoing. I just mentioned some major here, such as, for example, Norman Lerb in 21, which is discussing that this decadal increase in the Earth's energy imbalance from the mid-25 to 19 is from decreased reflection of energy back into space by clouds and also by sea ice, and increases in well-mixed greenhouse gases and water vapor. Then there's a discussion in the study from Kramer et al. In 21, all sky instantaneous radiative forcing has increased. And this is accounting for a positive trend in the total planetary radiative imbalance. And also here the argument is it's due to a combination of the rising concentrations of well-mixed greenhouse gases, but also for recent reductions in aerosol emissions. So there's another component discussion which is coming into play from this study. Then there's another one from Maran in 21, which implicitly demonstrates, while using climate model simulations, that it's not internal variability which is dominating this increase in the Earth's energy imbalance, and this can be attributed to anthropogenic influences. So there is still different controversy in terms of the different arguments, and there's further research needed. But all of the studies agree that we observe currently an increase in the Earth's energy imbalance, and hence in the Earth's heat inventory. So why should we care about all of this? What would be the sense? Of course, we are scientists, we are interested. But the accumulation of thermal energy in the Earth system is the root cause of the various facets of observed climate change. So this is just an older representation on the different impacts. So increasing the Earth's energy imbalance means increasing the impacts and increasing the changes in the Earth system, like a decrease in land ice and increase in ocean heat content, with then increase in global mean sea level, etc. Global surface temperature increase, extremes, etc. Here's another recent representation. We have provided a more full overview in this paper published yesterday. So again, we're stating that the accumulation of thermal energy over multiple decades resulting in unprecedented and committed change to the Earth system with adverse impacts for ecosystem and human systems. Of course, we need to approach the Earth inventory from a global scale perspective in order to derive the estimate, to understand the accumulation, to see how the different components act, and also to allow us for the observing system recommendations as we have done. But I think also we need to move ahead, and which opens a new opportunities in terms of research questions and improvements, for example, in climate models. If we also turn away and take this opportunity to understand the linkages between the different implications we know which occur today, because there is an increased Earth heat inventory due to an increased positive Earth energy imbalance. And this is addressing all Earth system components, such as the atmosphere, so increased atmospheric convection, extremes, weather extremes, changes in atmospheric circulation, increase in water vapor, atmospheric temperature. Then we have also in the cryosphere, permafrost extent, ice sheets, Arctic sea ice, etc. Then the increase in the ocean, increase in ocean mass, ocean temperature, decrease in carbon uptake, increase in marine extremes, increase in volume and sea level, and then also on land and flooding and erosion, soil respiration extremes, etc. So we have started with a long list, but I think this can be certainly improved. And also this together has been combined here, synthesized, which had been assessed in the Working Group 2 IPCC report. These are the impacts on the ecosystems, which changing ecosystem structures, changes in phenology, changes in species range shift, for example, or impacts on the human systems with city settlements and infrastructure changes, food production, and health and well-being. So increased impacts, sorry. So this is the synthesis in order to start a new dialogue in terms and to open new opportunities for research questions. So this is just a final comment. So I just synthesized together the numbers. I will not repeat them here with the synthesis of the figures on the different numbers, the increase in the Earth's heat inventory and hence the Earth's energy imbalance. And I would like to strike again that the Earth's heat inventory and hence the Earth's energy imbalance is one of the most fundamental global climate indicators, and something we specifically highlight in this community work, as that we call for an implementation of the Earth's heat inventory into the Paris Agreement global stocktake based on best available science. And this concerted international effort recommends archiving, rescuing, continuity, extension, and calibration efforts for the global climate observing system to enable sustained and improved global monitoring of the Earth's heat inventory. Thank you very much, and do not hesitate to ask me many questions. Thank you very much.
Okay, thank you very much. Do we have any questions? Yes, Gavin.
Hi, Karina. Thank you very much for the talk and the impressive amount of work that has gone into that paper, which I saw that came out yesterday. One of the questions that we discussed previously, and I think it might be interesting to have this discussion with everybody else here, is to what extent the simplifications or the completeness or the incompleteness of climate models allow us or don't allow us to match the observational trends in the overall energy imbalance. You know, I did some preliminary numbers on this, and I don't think it's a very big number, but it's not zero either. And so have you had any more thoughts on that, or do you want to like dig into that a little bit more?
Yeah, thank you very much for raising this question and allowing to extend this discussion on this topic. So yes, that is maybe a general comment, and what we have tried to, let's say, to change in terms of the use of this kind of information and the new questions we could raise on terms is, of course, if you look at from a global perspective on the heat inventory, those numbers are maybe forgettable small, and they maybe get under any uncertainties, evaluations, etc. But I think these numbers are completely very much important if you put them in a context in terms of what this means and what the implications are, because you have these numbers, these small numbers, in increased permafrost or in the ice sheets or etc. And these, I think, there are huge numbers. As I mentioned before, I mean, it's a simple example, but we need to continue to think about these aspects. But this, again, this 4% of the cryosphere, and it's even less because this 4% also includes the floating part. So maybe it's a 3%, and it's going on in this discussion on uncertainties, is responsible for 70% of global mean sea level rise. So, and this changes a bit the view. So, and also limitations in models. So one would need to see what the implications are that you miss some of those numbers. So what would you expect in terms of the implications in the change in the climate system, and in terms of the prediction of this, and how could maybe a constraint help to improve this? Are these implications a bigger part of the change? And then the second point is also to not look at the, let's say, the storage numbers, but on how they change over time. I think that is a completely new perspective as well, which would allow to answer many questions. So, for example, I have many questions for the last 2 decades with the questions in which state we are today.
Yes, thank you.
But what are your perspectives on this? To turn the question back to you.
Well, I mean, so, you know, the models are incomplete in many ways, right? So they don't generally have, I mean, our model, right, first doesn't have very deep soils. It doesn't include floating ice shelves as a dynamic part of the model. The connection to the dynamic ice sheets is, you know, still something that we're working on, and we have some energy issues associated with how you model those things. You know, the resolution that the models have doesn't allow for a lot in the way of mounting glaciers. And so changes in the energy associated with mounting glaciers are not really included in the model. And if you add up all of these things, what you end up with is there's less energy being buried in the model in places than there is in the real world, which means that the surface temperatures warm up faster for the same energy imbalance, and so therefore you would expect that the energy imbalance in a model that doesn't include all of these things would be slightly less than you would be anticipating in the real world. Now, you know, and you know, I'm not sure that it's the dominant reason. I'm pretty sure that it's not the dominant reason why the models seem to underestimate the increase in the energy imbalance over the series period. But I don't know that it's totally zero either, right? And so this is something that I think, you know, would be helpful to quantify in a couple of models at least, to see what's missing. You know, and that, I mean, there are also implications for the water budget, of course, because, you know, the models are not including many of the sources of fresh water, your static sea level, right? So they don't have, if they're not melting the glaciers because the energy is, well, because the glaciers aren't there, so then that energy goes into warming the surface, not melting the glaciers, and then that's a term which is important for the sea level, right? So you have to, so getting the sea level budget right and the energy budget right are connected. And working out how to do those things as best we can, both and slightly differently in the historical period where we've got some data, and slightly differently in the scenario period where we don't. It seems to me to be a very important role where, you know, this kind of analysis and assessments of the models could be very useful. Sorry, that was a bit rambling, but that's kind of what I'm thinking.
Yeah. And I would like to add another point for thinking on future discussion is, for example, many of them where you just say that the model doesn't include it or has some caveats are also aspects which are highly sensitive in terms of feedback mechanisms. So, for example, what would be the impact of missing, for example, the floating part of the ice, and also how they are melting, or in terms of the energy balance, in terms of leveraging then a feedback between the ocean and the uptake of heat, because you have open ocean then.
Well, exactly. So we
and also with the albedo from the glaciers and on. Sorry.
And I'm not sure that the albedo term really makes a big difference. The aerial changes in glaciers have not been large enough to really make that much of a big deal. But again, it's something that's worth looking into. But the impact of the melt on the ocean, that is something that's clearly an order one thing that most models, in fact, all of the models that are currently in the CMIP6 archive don't include. And so there's been a little bit of work on this, and we've just redone some experiments with putting in the freshwater melt terms from the changes in floating and ice shelf loss into the Southern Ocean, into Greenland, the seas around Greenland, to see what impact that has on the temperature trends and the sea ice. And in the Southern Ocean, it makes a difference, and it kind of puts you much closer to the observations where there's been this Southern Ocean cooling, and up until very recently, an increase in Antarctic sea ice. And that's something that you only match once you include the additional effects of Antarctic meltwater or Antarctic freshwater additions. So we can do that in a kind of not uncoupled sense, where we're not like expecting a perfect simulation of the ice dynamics itself, but we can kind of, for the historical period, we can kind of put it in the Deus Ex Machina. And that makes a difference, and then there's work that's being done that suggests, I'm not totally convinced by this, but that suggests that if you cool the Southern Ocean, then there's a kind of knock-on effect in the Eastern Pacific, where you end up with more cooling as well. There's a paper by Clara Dessa that's just been Kang et al. That's just been submitted on that kind of thing. And so it's quite possible that being more careful of the mass budget and the energy budget actually reduces the discrepancy between what the models are producing for the historical period in terms of the SST pattern changes, and therefore the cloud feedbacks, right? And all these things might in fact be connected. And so I think there's a lot of continuing work that needs to be done there to kind of pin that down, and getting, there's a lot of assumptions that, however you do it, there's a lot of assumptions. And so finding ways in which to test those assumptions against, your data is, I think, something that we could be doing. But yeah.
Yes, and vice versa. We would need to use urgently the model data in order to understand what is happening, what is going on here, because since with this huge increase we observe in the observations. And I'm just starting to look a bit more into depth and the different other Earth system components. And what I see concurrently is that, the sign of the other components, particularly for the cryosphere, are completely churning sign. So I don't know how important now this feedback measurement I was just talking about is responsible, also explaining parts. I mean, we have many approaches of this change, but it's quite impressive. So I think, and that's nothing we can answer with the observations. And so we need to collaborate here together to urgently understand what's going on here. Because, this is a huge change. So we need to understand what's happening.
Yes, absolutely.
So we did have a few questions in the chat.
Yes, I've seen, yeah. Should I start for Natasha? So thank
Yes.
you very much. Natasha is asking in terms of the uncertainties and the ocean heat content estimates and also projections. So I can mostly reply to on the estimates and also to have a clear knowledge on what the deep ocean is doing. There's normally if I orientate my presentations more for my expertise and heat content. So thank you for these questions and what the prospects are for these components. So I then also add normally what we can expect from this undersampled region. So I was stating before that for the ocean, we miss the shallow areas, we miss the deep ocean, and we miss polar areas. And so for the shallow areas, some studies have shown that this can really impact the estimate by about 10%. So we can have a reduced estimate of the trend by 10% if you do not use the shallow areas. For the deep ocean, there are some direct estimates which have been done, but there are, of course, with large uncertainties and for the very deep ocean from direct measurements. And so we have a value of what I've just said before of I think 0.5 or 0.6 of a very global scale. So we have, it's relative to this reduced ocean near global surface of the ocean. And so we have a contribution of about 0.1 from the deep, very deep ocean below 2000 meter depths. What the prospects are, there is a huge program which has been funded and which is called in terms of a so-called deep ocean arc component. There had been several test floats already deployed, which go down to 4,000 meter depths and some even to 6,000 meter depths, but it's still in the pilot state. So some floats had some problems. We are reaching also technical challenges because of the very deep the pressure components, but this is a project which is ongoing, and there had been some smaller, but there's not yet a global scale component for the shallow areas. And there are, of course, some components which look on floats and other measurements under ice to extend to the polar areas. There are also measurements from so-called sea mammals. So they have a CTD measurement on their head. We have started to look at this data as well, and they're really deep down. For example, in the Arctic area, you can find data down to 400 and even sometimes 1,000 meter depths, which is going to 90 degrees south, for example, really close to the shelf where it's going down. Yes, so this is also a project which is not sustained, and but there are some data. And then there's another from Anna Ruth, Halberstadt. Perhaps missed, but there's a heat going to the cryosphere separate from the heat going to warm the atmosphere and ocean, which in turn lead to ice mass loss. Separate, I mean, of course, we have an interaction. So it's separation, it's in terms of, I can maybe reply this question in terms of how we have calculated this. So we have really taken the assumptions of that the mass loss we observe in the cryosphere is directly linked to the heat available to melt the ice, and we have added different other assumptions also of heat conversion and latent heat. So I mean, if you want to separate this heat is in the Earth system, and then if this heat is in the Earth system, the different components have different characteristics, how they react, and so that's how it is redistributed. For example, then we have this large part in the ocean because of the huge heat capacity, and then we have this energy conservation physical part in the cryosphere to change the state and so on. And so I think that's more the way how I would explain this, but maybe I didn't fully get your question. Do you want to comment on this, or did it reply to your question? Okay, thanks. So I have a question from Ashley Bellas, and so did you hear this correctly, that climate models indicate the Earth's energy imbalance is very unlikely due to internal variability? If yes, then do we need climate models to make this argument? Maybe I give this question to Gavin. So this is something which has been also done from climate models in the paper here. I have cited, sorry, the wrong direction. Here. in Raman et al. So they have used this. So, but maybe for the second part of the question, I bounce back to Gavin.
Well, the issue is it's clear that you don't get an acceleration in the net Earth energy imbalance of anything like this length for this amount of time in internal runs, right? So you can remove you can conclude that it's not being driven by internal variability. But as you can see from the graph there, the estimates of the historical period, most of the models come in with about half of the acceleration and the energy imbalance that has been inferred from series. Now, you know, if you look at the individual runs, there's a little bit more of a spread. If you look at the runs that have more or different aerosol models, then you can see things that are a little bit better, right? So I think the models that have, well, in fact, I mean, the model that is closest to the net energy imbalance as derived from series is the GIST model with the most sophisticated aerosol scheme, and so that seems to suggest that that there are that part of this is related to aerosol changes, and our estimates of what those aerosol changes are not great, particularly in the CMIP archive, because they're not using observations past 2015, and the big discrepancy, not just in the net but also in the shortwave, really all happens after 2015. And so, you know, it's conceivable that aerosols have been falling faster than we anticipated 10 years ago, but we're really waiting on the updates of the aerosol and precursor emissions to be updated to like 2021, so that we can redo these estimates over time. So we haven't done that yet, and so unfortunately the comparisons of models to the energy imbalance for the last 20 years is imperfect in many ways. And so we're actually we just submitted a new protocol that we're calling Series MIP to update a whole bunch of different things and redo a lot of these analyses, and then I think we'll have a much better like-for-like comparison with both the series data and the energy fluxes that you've diagnosed, at least to 2020. I mean, things seem to go a little awry after 2015 in terms of expectations and observations, and it's not clear to me what particular thing happened after then, or what issues are arising after then that are causing some of these problems. You know, people have suggested, you know, the corrections to JSON3 might make a difference. People have suggested, you know, uncertainties in the aerosol forcing. You know, people have suggested that, you know, it's just the cloud feedbacks are kicking in now that we're like more than a degree above pre-industrial, and the models are just wrong on those things. All of those things are possible. So it's a very, I think we still need the climate models, if that was the question, because we need to be able to attribute all of these changes, and an attribution is a model-based exercise, not just a data-driven one.
Yes, and also to have a bit of further understanding, again, of course, for example, the aerosol aspect of having, which have been maybe now an increased impact, and hence have been reduced to restrictions. This is another discussion which is ongoing right now. So we have under-method warming we have observed before, etc. But the question is also what's happening again if you see such a decrease in the heat available to melt ice in some areas, and then in a concurrent increase. So you reduce then also, yeah. So there are some really big questions open in the way of terms of maybe the the forcing is linked to the ones which I discussed here, but the mechanism on how this is then impacted in the change in the Earth's heat inventory and the Earth's energy imbalance might be a different one. And I think analyzing these in the climate models would be also another way to understand this, which we can't do with the observations alone. Okay. Are there any other questions? Otherwise, I'm really perfectly on time. I'm quite proud.
Okay.
Yeah, thank you. I really enjoyed as well.
Very much. Everyone.